Today we're going to look at the applications that we have for our exponential equations. Today we're going to look at banking situations and population situations and other things that act in exponential sorts of ways. Your bank account acts in an exponential way. If you put in an initial amount of money and you put it at a certain interest rate for a certain amount of time, there is a formula that you can use to calculate how much money you'll have after a given number of years. And that equation is y equals, or the amount that you'll have at the end is equal to a, which is our initial amount, times, and in parentheses, 1 plus or minus r. Now the reason it's plus or minus is if this is also the equation for decay. Right? If something declines in a exponential fashion. So the growth is 1 plus r, decay is 1 minus r, and I have an example of both. Raised to the t power, and t is the amount of time in years. So let's see how we can apply that. So for our first example, we are depositing $500 at 12% per year for 3 years. So we plug in our initial amount of 500, plug that in for A, plug the 0.12 in for our rate, and remember we have to change percents to a decimal before I can use them, and then the amount of time was 3 years. Word of operation says I need to do what's inside the parentheses first, then do the exponent, then do the multiplication. And when you do that, you get $702.46. And of course, since this is a word problem, your answer needs to have some sort of label. Now let's look at a decay problem. So in this situation, we have a population that starts out at 100,000 and it is decreasing at 5% per year for 6 years. So how many people will be left? Well, again, our initial amount is 100,000. This is decay, so it's going to be 1 minus 0.05, and 0.05 is 5% as a decimal. 1 minus 0.05 to the 6th power, 6 years for the 6th power. Again, order of operations, 1 minus 0.05 to the 6th power times 100,000, and you should find that there are 73,509 people left. Now, banks don't always compound annually. Sometimes they compound more often than that. And when they compound more often than that, we have to modify our equation. We still have the y equals the a, and we still have 1 plus or minus. But now, since that rate is being, say it's happening 4 times a year, that rate is being divided 4 times into 4 different rates. Right? And 4 times the number of years will give us the number of times that it occurs. So if it happens 4 times and it lasts for 6 years, then that's 24 times that it gets compounded. So let's look at an example. Here, we are depositing 500 at 12% increase, and in this case it is compounded monthly. This is the same problem we had in the first problem, except that was compounded annually. This is compounded monthly for 3 years. So we'll again plug our 500 in for A. It is 1, this is an increase, so it's 1 plus, and then I take my 12% or 0.12 and I divide it by 12 inside the parentheses, and then I multiply the number of years times 12 on the outside. We multiply because now 36 times this is actually going to get compounded over that 3-year period. So again, order of operations, 0.12 divided by 12, add 1, raise it to the 36th power, take that answer and multiply it by 500. You should find that it would leave you with $715.38. which, if you go back and look, is more than it would be if it was compounded annually. Please make sure you fill out the WISC.